Hey everybody, and welcome to what I think is our last video here that we're going to do about our solutions unit. So we're here in the lab because I'm going to do a little bit of a demonstration later on with some of the stuff you see down over here. But what we're going to talk about are the materials known as colloids. And I think a good way to define colloid is to actually call it a homogeneous non-solution. So what do we mean by solutions, and what am I getting at when I call it a non-solution? So let's take a look at this quick little list of items I have here on the screen. So what we've been playing around with have been solutions. What are solutions? Solutions are homogeneous, which means when you and I look at them, they look like one continuous material. And even all the way down to all but the molecular or atomic level, it really does behave like one continuous solution. So to the naked eye, and even at a greater level of detail, it behaves as if it's homogeneous. On the other end of the spectrum, we would have materials like suspensions. And a suspension is, when you look at it with the naked eye, you can tell that it is made up of multiple materials. Think of something like, a glass of water with some sand in it, right? That's clearly two materials. Or think of those snow globes, right? You can shake up those snow globes and you can clearly see one material suspended in another. That's a suspension. Colloids reside in between those two extremes. So a colloid, to our naked eye, to our unassisted eye, is going to look homogeneous. It's going to look like a solution. It's going to look like, if it's colorless, it's just going to look like plain water, for example. But it does contain particles. There are particles suspended in the solvent that have some noticeable size when you start to look at under a little bit of magnification, or you do some other tests, as I'm going to do in a second here. So colloids, we're working with solute particles, although maybe we wouldn't call them solute because they're not dissolved in the typical sense, but solute particles that range from about 1 to 1,000 nanometers. Now you remember in our last unit when we did liquids and solids, we learned that molecules and atoms and unit cells exist at the 10th of nanometer size. So when we get to a nanometer, or tens of nanometers, hundreds of nanometers, thousands of nanometers, these materials, once put into a liquid, are going to be suspended, and they're going to behave a little bit different than solutions. And so these materials are called colloids. You actually have a lot of day-to-day experience with colloids. Perhaps you just didn't know the term. So I'm going to shrink this stuff down here, or at least move it down, maybe shrink it a little bit. And I'm going to bring over this table. This table lists a few different types of colloidal systems. And a colloid is defined based on what is being dispersed into what else. So we have the dispersed substance, the solute, and the dispersing medium, the solvent of sorts. For example, fog is a colloid. It's an aerosol, and what it is comprised of are little tiny droplets of water that are suspended in air, right? We've all seen fog, all right? When you look at fog, it's just kind of one continuous, layer of fog. So it kind of looks homogeneous to our naked eye. But if you could magnify it, you could see that there are noticeable water droplets suspended in air. How about foams? Whipped cream. Everybody likes whipped cream. Whipped cream is a case where what we have is a foam. So we have a gas getting dispersed in a liquid. You can make whipped cream at home. You get some heavy whipping cream, and you just really whip the heck out of it to get some air into it, and it turns into whipped cream that we can put on our ice cream or our squash pie, whatever it is we like. Milk is another example of a colloid. It's an emulsion where we have sort of short chains of fat suspended in water. It's a liquid-liquid colloid called an emulsion. Paints are also colloids. We have tiny pigments, tiny molecules of paint, or they could be, other materials being suspended in the liquid that is the base of the paint. So you have everyday experience with colloids. You see these things quite frequently, and some of them, as you can see, actually taste pretty darn good. There are plenty of other examples. You can look in your textbook and you can see a longer, larger, more detailed list of other colloids. So I'm going to do a little demonstration for you. So like I said, when you look at a colloid, to your naked, unaided eye, it looks like a solution. And I have here two examples of solution-like materials. One of these materials is actually just yellow food dye that I added to some water. And the other material is actually a colloid of silver nanoparticles that are on the order of about maybe 10, 20, maybe not quite 100 nanometers in size, little globs of silver. Okay? We can actually test for the presence of a colloid using something called the Tyndall Effect, T-Y-N-D-A-L, the Tyndall Effect. And essentially, you can see the Tyndall Effect when you're driving at night on a foggy night. You know how sometimes when you turn headlights on as you're driving into the fog, the light almost bounces right back at you and you can barely see in the fog because the light is getting reflected back at you? Well, that's because as the light hits some of the water particles that are suspended in the air, it bounces back at you. So colloids have suspended particles that are large enough to cause some bending of the light. You can see the haze of the light being bounced back at you. So I've got these two systems here, and we're going to try to figure out which one of them is a colloid. All right, so I'm going to take this guy here, this yellow solution, and I have here a fairly highly powered laser pointer. And what I'm going to do, and maybe you can see, okay, right, there's the green laser. I'm going to shoot the green laser through my solution or colloid, whatever this might be. And in this case, as it goes through, you don't see a whole heck of a lot. You might see the occasional glint of green light inside the yellow liquid because there's some dust in there, and so occasionally it bangs into a dust particle, so you might catch a little bit of a glint of dust every now and then. But otherwise, this green light is going right through without really doing anything interesting. So this doesn't look all that interesting. But this material here, as I shine my green laser through this, something cool is going to happen. As you can see, right, we are actually able to see the line of the laser go through this material. So that tells me that this guy is a colloid because it's demonstrating the Tyndall effect. I can see the light getting bounced around as it passes through this colloid because it's banging into some of the larger colloid particles, causing the light to be bent in a direction that you can see. All right, so that's kind of cool. So if I put them both here on the table, let me put them in a spot where you can clearly see them. All right, and I'll shine the laser through, right? It gets bounced around in the colloid, but it goes right through the solution. Or if I put the solution in front, it'll go right through the solution, but it gets bounced around in the colloid. So again, that's called the Tyndall effect. And it's a way with a fairly simple piece of equipment where we can determine the particle size of our materials. So I can't give you a specific value for the particle size, but I know that beaker over here, that vial over here, has particles that are clearly larger than 1 or 2 or 10 nanometers because I'm seeing the Tyndall effect. All right? So that's a little bit about colloids. They're materials that are involving solutes that are smaller than those found in suspensions, but noticeably larger than those found in a simple homogeneous solution. All right, that's it for our solutions unit. We'll see you next time when I think we're going to pick up our conversations on electrochemistry. All for now.